Big Freeze, also known as the heat death of the universe, is a fascinating concept in cosmology. It presents a scenario where the universe continues to expand forever, leading to a state of maximum entropy, which means that all energy will be evenly distributed and no thermodynamic free energy will be available to do work. As the universe expands, galaxies will drift farther apart, and stars will eventually exhaust their nuclear fuel, leading to a dark, cold universe filled with remnants of stars, such as white dwarfs, neutron stars, and black holes. Over unimaginable timescales, even these remnants will fade away, leaving behind a faint glow of radiation, which will also dissipate as the universe cools down to absolute zero. One of the key ideas related to the Big Freeze is the concept of dark energy, a mysterious force that is thought to be driving the accelerated expansion of the universe. Discovered in the late 1990s, dark energy makes up about 70% of the total energy density of the universe, and its nature remains one of the biggest unsolved mysteries in physics. The acceleration caused by dark energy means that galaxies are moving away from each other at an ever-increasing rate, which leads to the eventual isolation of galaxy clusters and the fading of the night sky as fewer and fewer stars are visible from any given point. The timeline for the Big Freeze is staggering, with estimates suggesting that in about 100 trillion years, or even longer, most stars will have burned out, leading to a dark universe dominated by black holes and cold remnants. Even black holes themselves will not last forever. They are expected to evaporate over incredibly long timescales due to a process called Hawking radiation, theorized by physicist Stephen Hawking. This radiation allows black holes to lose mass and energy, ultimately leading to their slow demise, which could take up to a quadrillion years. As the universe continues to expand, it will reach a point where galaxies will be so far apart that they will no longer be able to interact with each other, leading to a vast, empty space where the only remnants of the past will be the occasional rogue star or a lonely neutron star drifting in the cold void. This scenario raises intriguing questions about the fate of life in the universe, as the conditions for life depend on energy sources, which will be extinct in a cold, dark universe. The Big Freeze serves as a stark reminder of the impermanence of everything in The Big Crunch, is one of the fascinating theories concerning the ultimate fate of the universe, suggesting that, after expanding for billions of years, the universe may eventually stop expanding and start contracting, leading to a collapse into a singularity. This idea arises from the understanding of gravity and the dynamics of cosmic expansion, which is influenced by the density of matter and energy in the universe. According to this theory, if the overall density of the universe is greater than a specific critical value, the gravitational attraction of all the matter within it would eventually overcome the current expansion driven by dark energy, which is a mysterious force that seems to be causing the universe to accelerate in its expansion. As the universe contracts, galaxies, stars, and planets would draw closer together, and the distances between them would shrink, leading to a scenario where everything might collide into a dense, hot state, much like the conditions believed to exist at the very beginning of the universe, during the Big Bang. In this scenario, as the universe condenses, temperatures would rise dramatically, causing matter to behave in ways that are difficult to predict, leading to extreme physical conditions. Theoretical physicists have pondered what might happen during this cosmic collapse, with some suggesting that it could result in a series of violent events, such as the merging of galaxies and the formation of massive black holes, all while the universe's structure becomes increasingly chaotic. Ultimately, the Big Crunch would culminate in a singularity, a point where our current understanding of physics breaks down, and the laws of nature as we know them may no longer apply. This idea raises intriguing questions about the nature of time and space, as well as the potential for a cyclical universe, where a big crunch could lead to another Big Bang. While the Big Crunch remains a captivating possibility, it is essential to note that current observations indicate that the universe's expansion is accelerating, primarily due to dark energy, leading many scientists to consider alternative scenarios, such as the Big Freeze, where the universe continues to expand indefinitely, growing colder and more isolated over time. However, the Big Crunch theory continues to inspire discussions about the universe's fate, prompting researchers to explore the fundamental laws of physics and the nature of cosmic evolution. As we delve deeper into the cosmos, utilizing advanced telescopes and observing distant galaxies, scientists hope to gather more data to refine our understanding of the universe's ultimate destiny, exploring the balance between expansion and contraction and the intriguing interplay of forces. The Big Rip is a fascinating concept in cosmology, proposing a dramatic and somewhat unsettling fate for the universe. According to this theory, the universe could end not with a bang, but with an expansion so rapid and extreme that it tears apart galaxies, stars, planets, and even atoms themselves. This idea stems from the observation that the universe is not just expanding, but that this expansion is accelerating, a phenomenon attributed to a mysterious force known as dark energy. Scientists believe that dark energy makes up about 70% of the universe, yet its true nature remains one of the biggest mysteries in modern physics. The Big Rip scenario suggests that if the density of dark energy increases over time, it could eventually overcome all gravitational and electromagnetic forces holding matter together. As this acceleration continues, galaxies would begin to move away from each other at an ever-increasing speed. Eventually, this would lead to the destruction of galaxy clusters as the space between them stretches. Over time, even stars would find themselves unable to hold on to their planetary systems, as the forces keeping them bound would be outmatched by the relentless push of dark energy. As we consider the implications of the Big Rip, it becomes even more dramatic, with the very fabric of space and time potentially unraveling. In the final moments of this cosmic event, the forces would become so extreme that even atoms could be torn apart, resulting in a universe where everything is scattered and disintegrated. The timeline for such an event is theorized to be billions of years in the future, with estimates suggesting that it could occur in about 20 billion years, depending on the behavior of dark energy. The Big Rip poses interesting questions for scientists and philosophers alike, as it challenges our understanding of existence and the ultimate fate of all things. It raises profound questions about the nature of reality, the universe's structure, and our place within it. While the Big Rip is just one of several theories about the universe's end, such as the Big Crunch or heat death, it captures the imagination because of its sheer scale and the dramatic imagery it evokes. He understood the delicate balance of forces that shape our universe. The heat death of the universe is a fascinating, albeit somewhat chilling concept within cosmology, stemming from the second law of thermodynamics, which states that in a closed system, entropy, or disorder, will always increase over time. This means that, as the universe continues to expand, energy will become more uniformly distributed, leading to a state where no useful energy remains to perform work. Picture a scenario where the stars have burned out, galaxies drift apart, and matter becomes incredibly diffuse. In this distant future, the universe will reach a state of maximum entropy, where temperatures are nearly uniform, hovering just above absolute zero, around minus 270 degrees Celsius, or minus 459.67 degrees Fahrenheit. In such a universe, life as we know it would be impossible, as there would be no energy gradients to sustain processes. All stars would have exhausted their nuclear fuel, leading to a dark, cold expanse filled with remnants like black holes, neutron stars, and faint clouds of gas. The idea of heat death raises intriguing questions about the fate of everything we know, as it suggests a slow, inexorable decline into a lifeless void. Some scientists estimate that this state could occur in over 1 trillion years, far beyond the current age of the universe, which is about 13.8 billion years. 1. Interesting aspect of the heat death theory is the role of black holes. Over immense timescales, they are expected to evaporate through a process known as Hawking radiation, named after the theoretical physicist Stephen Hawking. As they lose mass, black holes will eventually disappear, contributing to the overall increase in entropy, but this process takes an extraordinarily long time, on the order of billions of times the current age of the universe. The concept of heat death also invites comparisons with other theories about the universe's fate, such as the Big Crunch, where the universe might eventually stop expanding and start contracting, leading to a collapse. However, current observations suggest that the universe's expansion is accelerating, making heat death a more likely outcome. This scenario is not just theoretical, it has implications for our understanding of time, space, and the fundamental laws of physics. Moreover, discussions around the heat death of the universe often intersect with philosophical questions about existence and the nature of time. If everything eventually reaches a state of equilibrium, what does that mean for concepts like change and life? The heat death serves as a reminder of the impermanence of all things. Quantum fluctuations, a fascinating aspect of quantum mechanics, refer to the temporary changes in energy that occur in empty space, even when no particles are present. This phenomenon arises from the uncertainty principle, which states that we cannot precisely know both the position and momentum of a particle simultaneously. In essence, these fluctuations are the result of virtual particles popping in and out of existence, existing for such brief moments that they cannot be directly observed, yet they have measurable effects on the universe. One of the most remarkable implications of quantum fluctuations is their role in the creation of the universe itself, as they are thought to have contributed to the rapid expansion during the Big Bang, a process known as inflation. During this time, tiny fluctuations in energy density, which occurred on a quantum scale, became amplified, leading to the large-scale structures we observe today, such as galaxies and clusters of galaxies. Additionally, quantum fluctuations are not limited to the early universe. They also play a significant role in various modern technologies. For example, they are fundamental to the functioning of semiconductors, which are crucial for most electronic devices, including smartphones and computers. In these materials, quantum fluctuations can lead to changes in the electrical properties, influencing how devices operate. Moreover, researchers are exploring quantum fluctuations in the context of quantum computing, where harnessing these fluctuations could lead to advancements in processing power and information storage, potentially revolutionizing the field. Another intriguing aspect of quantum fluctuations is their connection to the concept of vacuum energy. The vacuum of space, which might seem empty, is actually teeming with these fluctuations, leading to a non-nino energy density, even in a perfect vacuum. This has implications for cosmology, particularly regarding dark energy, the mysterious force driving the accelerated expansion of the universe. Some theories suggest that vacuum energy, linked to quantum fluctuations, could provide an explanation for this phenomenon, although the exact nature of dark energy remains one of the biggest mysteries in physics today. Furthermore, quantum fluctuations have been observed and measured in laboratory experiments, providing evidence for their existence and effects. One famous experiment involves the Casimir effect, which demonstrates how two uncharged parallel plates placed very close together in a vacuum will experience an attractive force due to the restrictions on virtual particles between them. This is a direct consequence of quantum fluctuations, showcasing how they can have tangible effects in the physical world. In summary, the realm of quantum fluctuations offers a glimpse into the strange and counterintuitive nature of the universe at a fundamental level. From influencing the cosmic inflation is a fascinating theory that explains the rapid expansion of the universe right after the Big Bang. This idea suggests that in a tiny fraction of a second, the universe expanded exponentially, growing from subatomic scales to about the size of a grapefruit, all while the cosmos was still incredibly hot and dense. This expansion was not just a slow stretching, but rather a dramatic and explosive increase in size, which helps to explain why the universe appears so uniform and isotropic on large scales today. One of the key pieces of evidence for cosmic inflation comes from the cosmic microwave background radiation, which is the afterglow of the Big Bang, filling the universe with a faint, uniform glow, and it shows a surprising level of uniformity, suggesting that different regions of the universe were somehow connected in those early moments. The theory of inflation was first proposed by Alan Guth in the 1980s, and it takes into account ideas from quantum mechanics and general relativity, suggesting that a field, known as the inflaton field, drove this rapid expansion. This inflaton field is thought to have had a high energy state that caused a repulsive gravitational effect, leading to the swift expansion we call inflation. After this phase of inflation ended, the inflaton field decayed into particles, which contributed to the matter and radiation that would later form galaxies, stars, and eventually planets. The theory also helps to address some of the shortcomings of the Big Bang model, the flatness problem and the horizon problem, which question why the universe is so uniform and flat when it seems like there wasn't enough time for light to travel between distant parts of the universe. Cosmic inflation has undergone various refinements and modifications over the years, with different models proposing various dynamics of the inflaton field. Some versions suggest that inflation could happen multiple times in different regions of the universe, leading to a multiverse scenario where our universe is just one of many, each with different physical laws and constants. This idea opens intriguing questions about the nature of reality and the structure of the cosmos, igniting the imagination of scientists and enthusiasts alike. Moreover, current research into cosmic inflation continues to be a vibrant field of study, with experiments like the BICEP and Planck satellites working to measure the polarization of the cosmic microwave background radiation for evidence of gravitational waves that could have been produced during inflation. Detecting these waves would provide significant support for the inflation A vacuum metastability event, often abbreviated as VME, is a fascinating concept in the realm of particle physics and cosmology, relating to the stability of the vacuum state of the universe. In simple terms, our universe exists in what we call a vacuum state, which is a low-energy state, but it might not be the absolute lowest energy state possible. The idea is that there could be a lower energy vacuum, and if our universe were to transition to that state, it would result in dramatic and catastrophic changes to the laws of physics as we know them. This transition might occur through a process called quantum tunneling, where particles can jump through energy barriers, leading to a sudden change in the vacuum state. When considering the implications of a vacuum, the metastability event, one must think about how such an event could affect everything from the formation of atoms to the structure of space-time itself. If the vacuum were to shift to a lower energy state, it could create a bubble of this new vacuum that expands at the speed of light, fundamentally altering or destroying everything in its path. This scenario raises profound questions about the very nature of our universe, as well as our understanding of physics. Furthermore, researchers have speculated that this event could potentially happen, albeit very unlikely in the near future, given the current stability of our vacuum state. Models of particle physics, particularly those involving the Higgs boson, suggest that our universe is sitting precariously on the edge of stability, which adds an intriguing layer to the study of fundamental forces and particles. The Higgs field, for instance, is associated with the mass of elementary particles, and fluctuations in this field could be linked to the possibility of a vacuum metastability event, signaling that the fabric of our reality may not be as solid as we perceive. Cosmologists and physicists continue to explore the implications of such phenomena, examining the potential for a catastrophic transition to a new vacuum state, while also investigating the conditions under which such an event could occur. This leads to discussions about the ultimate fate of the universe and the long-term stability of what we consider to be reality. The idea of a vacuum metastability event challenges our understanding of existence and compels us to think deeply about the universe we inhabit, pushing the boundaries of scientific inquiry and philosophical thought. It's a reminder that, even at the most fundamental level, our universe is full of surprises, and the quest for knowledge continues to unfold. Dark energy, a mysterious force that makes up about 70% of the universe, is one of the most intriguing topics in modern astrophysics. Discovered through observations of distant supernovae, scientists realize that the universe's expansion is not slowing down, as once thought, but is actually accelerating. This acceleration suggests that some unseen energy is pushing galaxies apart, and that's where dark energy comes into play. Unlike normal matter, which makes up stars, planets, and galaxies, dark energy does not interact with electromagnetic forces, meaning it does not emit, absorb, or reflect light, making it extremely difficult to detect directly. Instead, its effects can only be observed through its influence on the cosmos. One of the key effects of dark energy is its role in the large-scale structure of the universe. As the universe expands, dark energy counteracts the force of gravity, which tries to pull matter together. This delicate balance between gravitational attraction and dark energy's repulsive force has profound implications for the fate of the universe. If dark energy continues to dominate, the universe may continue to expand forever, leading to a scenario known as the Big Freeze, where galaxies drift apart and stars eventually burn out, leaving behind a cold, dark cosmos. In contrast, if dark energy were to decrease over time, gravity could take over, potentially leading to a big crunch, where the universe collapses back into a singular point. However, current observations suggest that dark energy remains constant, or at least behaves in a way that supports the idea of perpetual expansion. The discovery of dark energy has also led to the development of various models, such as the cosmological constant, proposed by Albert Einstein, which treats dark energy as a constant energy density filling space homogeneously. Moreover, dark energy is not just a concept limited to cosmology. Far-reaching implications in other fields of physics and philosophy. It challenges our understanding of fundamental physics, prompting questions about the very nature of space and time. Some theories even suggest that dark energy could be a sign of new physics beyond the standard model, hinting at a deeper understanding of the universe. Scientists are continuing to investigate dark energy through large-scale surveys, like the Dark Energy Survey and the European Space Agency's Euclid mission, both of which aim to map the distribution of galaxies and study how dark energy influences their movement. By gathering more data, researchers hope to unravel the mysteries surrounding dark energy, potentially leading to new discoveries about the fundamental forces. The gravitational collapse of stars is a fascinating process that occurs in the life cycle of massive stars, leading to some of the most spectacular phenomena in the universe, such as supernovae and black holes. A star has burned through its nuclear fuel. It can no longer support itself against the force of gravity, which pulls everything inward. This gravitational pull becomes increasingly powerful as the core of the star contracts, causing temperatures and pressures to rise dramatically. In stars with sufficient mass, This process can lead to the formation of a neutron star, or even a black hole, depending on the original mass of the star. As the core collapses, it heats up to millions of degrees, allowing for new nuclear reactions to occur, which can create heavier elements. This part of the process is critical, as it is during these moments that elements like iron are formed, which are essential for the creation of planets and, ultimately, life. Meanwhile, the outer layers of the star may be expelled violently, resulting in a supernoval explosion. This explosion not only enriches the surrounding space with heavy elements, but it also can trigger the formation of new stars in nearby gas clouds, continuing the cycle of stellar evolution. Interestingly, the fate of a star after gravitational collapse greatly depends on its mass. For instance, stars with a mass greater than about 3 solar masses will typically collapse into a black hole, where the gravitational pull is so strong that not even light can escape, while stars with lower mass may end up as neutron stars, incredibly dense remnants that emit radiation detectable as pulsars. There are also other outcomes for less massive stars, which may end their life cycle as white dwarfs, slowly cooling down over billions of years. The study of gravitational collapse also has implications beyond stellar life cycles. It plays a crucial role in the understanding of cosmic structures, such as galaxies. The collapse of gas and dust in the early universe led to the formation of stars and galaxies, showing how interconnected these processes are on a cosmic scale. Moreover, researchers continue to explore how the gravitational collapse of stars contributes to phenomena like gravitational waves, which were first detected in 2015, providing a new way to observe the universe and understand its complex dynamics. This gravitational collapse not only shapes the life and death of stars, but also influences the very fabric of the cosmos itself, making it a captivating topic for anyone interested in astronomy and astrophysics. In the vast universe, the concepts of singularity and black holes pique the curiosity of many, as they represent some of the most mysterious and extreme phenomena in astrophysics. A singularity, which is often described as a point in space where the gravitational forces are so intense that space-time curves infinitely, is a key feature of black holes. But what exactly does this mean? When a massive star exhausts its nuclear fuel, it can no longer support itself against the force of gravity, leading to a dramatic collapse. This collapse results in a singularity at its core, where the laws of physics as we know them cease to function normally, creating a region of infinite density. Surrounding this singularity is the event horizon, which is the boundary beyond which nothing, not even light, can escape the gravitational pull of the black hole. This means that once any matter crosses the event horizon, it is lost to the outside universe, making black holes fundamentally invisible to us. Interestingly, black holes can be classified into several categories based on their mass. Stellar black holes, which form from the remnants of massive stars, typically have masses ranging from about 3 to several tens of solar masses. Then, there are supermassive black holes, which reside at the centers of galaxies, including our own Milky Way. These monsters can have masses equivalent to millions or even billions of suns. The precise mechanisms that lead to the formation of supermassive black holes are still a subject of intense research, with theories suggesting they might grow from smaller black holes merging together, or from massive gas clouds collapsing directly into a singularity. Another fascinating aspect of black holes is their role in the universe's structure. They can influence star formation and the dynamics of galaxies due to their immense gravitational pull. The energy emitted as matter spirals into a black hole can be incredibly high, often producing jets of particles that can be observed from great distances. This process contributes to our understanding of some of the most energetic phenomena in the universe, such as quasars, which are powered by supermassive black holes consuming large amounts of material. Moreover, the study of black holes raises intriguing questions about the nature of time and space. According to Einstein's theory of relativity, As one approaches a black hole, time appears to slow down significantly relative to a distant observer. This phenomenon, known as gravitational time dilation, implies that if you were to hover near a black hole and then return to a distant point in space, you could effectively age. Multiverse theory, a fascinating concept in modern physics and cosmology, suggests that our universe might be just one of many, perhaps an infinite number of universes, each with its own unique properties and laws of physics. This idea arises from several scientific theories, including quantum mechanics and cosmic inflation, which propose that every possible outcome of a quantum event actually occurs, leading to the existence of parallel universes. Imagine a scenario where every choice you make spawns a new universe, creating countless variations of realities, where different versions of you might be living out alternate lives, making different decisions and experiencing different outcomes. One of the most popular interpretations of multiverse theory comes from quantum mechanics, specifically the many worlds interpretation, which was proposed by physicist Hugh Everett, EWF, in the 1950s. According to this interpretation, every time a quantum event takes place, such as an electron being in one state or another, the universe split into separate branches, each representing a different outcome. This means that there is a universe where you chose to go left instead of right, where you took that job offer, or where you decided to stay in school instead of traveling. In addition, the concept of cosmic inflation, which explains the rapid expansion of the universe just after the Big Bang, introduces the idea that different regions of space could stop inflating at different times, leading to the formation of bubble universes. Each bubble could have its own distinct laws of physics, making them vastly different from our own universe. Some might have different fundamental forces, different constants, or even different dimensions, creating an incredibly rich tapestry of existence. These ideas have sparked vibrant discussions among scientists, philosophers, and even writers, as they challenge our understanding of reality and raise questions about existence itself. Is it possible that there are universes where life forms are completely different from what we know, or where historical events occurred differently? Such possibilities ignite the imagination, leading to creative explorations in literature, movies, and art. However, multiverse theory also faces significant challenges. One of the main criticisms is the lack of direct evidence for the existence of these other universes, making it difficult to prove or disprove the theory. Despite the steady-state theory, a fascinating concept in cosmology, proposes that the universe is eternal and unchanging on a large scale, even though it is expanding. This theory was first introduced in the 1940s by scientists Fred Hoyle, Thomas Gold, and Hermann Bondi, who sought to explain the universe without the need for a beginning or an end. According to steady-state theory, as the universe expands, new matter is continuously created to fill the gaps left by the moving galaxies, maintaining a constant density over time. This idea contrasted sharply with the Big Bang theory, which suggests that the universe began from a singular point and has been expanding ever since. One of the main implications of steady-state theory is the notion of a perfect cosmological principle, which argues that the universe looks the same at all times and in all places, a belief that fundamentally challenges our understanding of time and change. Though it was initially a popular theory, steady-state theory has faced significant challenges, particularly from observational evidence. For instance, the discovery of cosmic microwave background radiation in the 1960s provided strong support for the Big Bang theory, as it suggested a hot, dense origin of the universe. Additionally, observations of distant galaxies showed that they were younger and more primitive, indicating that the universe has evolved over time, rather than remaining static, as steady-state theory would suggest. Despite its decline in popularity, steady-state theory has left a lasting impact on the field of cosmology. It prompted scientists to think deeply about the nature of the universe and sparked debates that helped refine our understanding of cosmic evolution. Moreover, the theory's emphasis on the continuous creation of matter led to various discussions around the conservation of energy and matter in the universe, which are critical concepts in physics. Interestingly, some modern theories, including certain interpretations of quantum mechanics, have drawn parallels to ideas found in steady-state theory, suggesting that, while it may not fully explain our universe, its legacy endures in the ongoing exploration of cosmic mysteries. The quest to understand the universe's origins and ultimate fate continues to inspire scientists as they investigate the fundamental laws governing our reality, raising questions about the very fabric of existence and whether our universe is truly unique or part of a larger multiverse. The final state of matter, often referred to as Bose-Einstein condensate, is a fascinating and complex phase that occurs under extreme conditions, specifically at temperatures close to absolute zero, which is around minus 273.15 degrees Celsius or 0 Kelvin. In this state, a group of atoms is cooled to such low temperatures that they begin to occupy the same space and quantum state, essentially behaving as a single quantum entity. This phenomenon was predicted by the Indian physicist Satyendranath Bose and the famous physicist Albert Einstein in the early 20th century, and it wasn't until 1995 that scientists were able to create this state in the lab, using a combination of laser cooling and magnetic trapping techniques. When atoms reach this state, they lose their individual identities and their wave functions overlap, leading to unusual properties such as superfluidity, which allows the substance to flow without viscosity. Bose-Einstein condensates can be created using different types of atoms, but rubidium-87 is the most common choice due to its favorable properties. Interestingly, this state of matter demonstrates a unique behavior that challenges our everyday understanding of solid, liquid, and gas states. For instance, in a Bose-Einstein condensate, the atoms are so closely packed that they exhibit collective behavior, which can lead to phenomena such as the ability to flow without friction. This state of matter has implications for quantum mechanics and helps physicists understand the fundamental nature of matter and energy. Research into Bose-Einstein condensates continues to expand, with scientists exploring their potential applications in quantum computing, precision measurement, and even in the development of new materials. The study of this final state of matter offers insights into the behavior of particles at extremely low temperatures, and it raises intriguing questions about the nature of reality itself. As we delve deeper into quantum physics and the behavior of matter at its most fundamental level, the Bose-Einstein condensate stands as a testament to the extraordinary and often counterintuitive world of quantum mechanics, highlighting the interplay between temperature, particle behavior, and the forces that govern the universe. Entropy, a fundamental concept in thermodynamics, is often described as a measure of disorder or randomness in a system, but it also reflects the amount of energy that is unavailable to do work. In simpler terms, it's about how energy spreads out and how systems evolve over time. According to the second law of thermodynamics, in any energy transfer or transformation, the total entropy of an isolated system can never decrease over time, meaning that natural processes tend to move towards a state of greater disorder, which is a bit counterintuitive, but has profound implications for everything from the life cycle of stars to the aging of living organisms. For instance, when you boil water, The heat energy increases the movement of water molecules, which leads to a more chaotic state, demonstrating how energy input can drive systems towards higher entropy. The first law of thermodynamics, also known as the law of energy conservation, states that energy cannot be created or destroyed, only transformed from one form to another. This means that the total energy of a closed system remains constant, even as it changes forms, such as when chemical energy in food is converted into kinetic energy when we move. This interplay between the first and second laws illustrates how energy flows through systems, and it helps us understand everything from engines to ecosystems. As energy transforms and entropy increases, shaping the universe as we know it. In practical applications, the concept of entropy has far-reaching implications. For example, in information theory, entropy is used to measure uncertainty or the amount of information contained in a message. The higher the entropy, the more unpredictable the information, which can be crucial for data compression and encryption. Similarly, in the field of chemistry, understanding entropy helps predict the direction of chemical reactions. As reactions tend to favor products with higher entropy, this means that reactions that produce gases or that result in increased molecular disorder are more likely to occur spontaneously. Moreover, the idea of entropy is not just limited to physical systems, but can also be applied to social and economic systems. For instance, in economics, the concept can illustrate market trends and consumer behavior, as markets tend to move towards equilibrium, where resources are allocated efficiently, reflecting a state of higher entropy in terms of information and resource distribution. This perspective allows economists to analyze how systems evolve over time, emphasizing the role of energy and information flow in shaping our world. Furthermore, the study of entropy has important implications for understanding the future of our universe. As the universe continues to expand, it is expected that time dilation is a fascinating concept in the realm of physics. Particularly within the framework of Einstein's theory of relativity, which suggests that time is not a constant, but rather it can vary depending on speed and gravitational fields. To put it simply, as an object moves faster, especially as it approaches the speed of light, time for that object slows down relative to a stationary observer. This means that astronauts traveling in a spacecraft at high speeds would age more slowly compared to people on Earth, which sounds like something out of science fiction, but is very much grounded in scientific reality. The implications of time dilation stretch far beyond just the aging of astronauts. It raises profound questions about the nature of time itself. For instance, if time can pass differently for people in different frames of reference, then it challenges our understanding of simultaneity. Two events that appear to happen at the same time from one perspective might not be simultaneous from another perspective, depending on the relative speeds of the observers. This has significant consequences for areas such as GPS technology, which relies on accurate time measurements. The satellites orbiting Earth experience time slightly differently due to their speed and the weaker gravitational field compared to the surface of the planet. Engineers must account for these differences, correcting the time signals sent from the satellites so that GPS devices on Earth can pinpoint locations accurately. Moreover, time dilation also has intriguing philosophical implications. It invites us to reconsider our perception of time as a linear progression, leading to discussions about the nature of reality, existence, and even the possibility of time travel. While time travel remains a theoretical concept, the idea that one could hypothetically travel into the future by moving at speeds close to light speed is an exhilarating thought. This notion has been explored in various forms of media, from literature to film, stimulating public interest and imagination regarding the fabric of time. In the context of black holes, time dilation becomes even more pronounced. As one approaches a black hole, the gravitational pull becomes incredibly strong, causing time to slow down dramatically relative to an observer far away. This means that if someone were to fall into a black hole, they would experience time differently compared to someone watching from a safe distance. The closer they get to the event horizon, the more pronounced the effects of time dilation would become, leading to the bizarre conclusion that they might appear to freeze in time from the perspective of an outside observer. In practical applications, scientists have conducted experiments using atomic clocks on aeroplanes and satellites, verifying the effects of time. Galaxies, those vast collections of stars, gas, dust, and dark matter, follow a fascinating life cycle that spans billions of years, beginning with their formation in the early universe. Shortly after the Big Bang, initially small fluctuations in density in the primordial gas led to the gravitational collapse of gas clouds, forming the first stars, and these stars clustered together, creating the first galaxies. Over time, galaxies continue to evolve, merging with other galaxies, which can lead to larger structures known as galaxy clusters. This process of merging is a key aspect of a galaxy's life cycle, as it can trigger new waves of star formation, increasing the galaxy's overall brightness and altering its shape. As galaxies age, they go through significant transformations. A spiral galaxy, for example, may start with a bright, well-defined structure with arms of stars and gas swirling around a central bulge. However, as the galaxy exhausts its gas supply, star formation slows down, and the galaxy can evolve into a more elliptical shape, where the stars are older, and there's less gas and dust to form new stars. This transformation can take billions of years, and the final result is a galaxy that is often more uniform in appearance and less dynamic than its earlier spiral form. Another interesting aspect of a galaxy's life cycle is the role of supermassive black holes, often found at the centers of galaxies. These black holes can influence the behavior of stars in the surrounding area, and they can also produce powerful jets of energy that impact star formation rates. When a galaxy merges with another, the dynamics change significantly, and the black holes can also merge, leading to the emission of gravitational waves, ripples in space-time that have only recently been detected by scientists. Additionally, the environment surrounding a galaxy plays a crucial role in its life cycle. Galaxies in dense clusters may interact more frequently with their neighbors, leading to phenomena such as ram pressure stripping, where the intergalactic medium strips away gas from the galaxy, thereby inhibiting star formation. Conversely, isolated galaxies have a different evolutionary path, often maintaining their gas supply longer, allowing them to continue forming new stars over extended periods. The end stages of a galaxy's life cycle can also be quite dramatic. In some cases, galaxies can experience a death phase where they become passive, red galaxies that no longer form stars. This can happen due to various factors, including the loss of gas, interactions with other galaxies, or dark matter. Is one of the most intriguing topics in modern astrophysics, capturing the imagination of scientists and enthusiasts alike. While ordinary matter, which makes up stars, planets, and everything we can see, accounts for only about 5% of the universe, dark matter is believed to comprise approximately 27%. This mysterious substance does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Scientists first inferred its existence in the early 20th century, when they noticed that galaxies were rotating at speeds that could not be explained by the visible matter alone. If only the visible mass were considered, the outer stars in galaxies would be flying off into space. Yet, they remain bound together, suggesting there is something else exerting gravitational pull. One of the key roles of dark matter is in the formation and structure of the universe. It serves as a scaffolding for galaxies, providing the necessary gravitational force that allows ordinary matter to clump together and form stars and galaxies. Theoretical models suggest that dark matter forms large halos around galaxies, influencing their formation and evolution. As galaxies formed, they likely drew in the surrounding dark matter, which created a gravitational well that helped gather gas and dust, leading to star formation. This process has shaped not just individual galaxies, but large-scale structures like galaxy clusters and superclusters, which are the largest known structures in the universe. Moreover, dark matter plays a crucial role in cosmic background radiation, which is the afterglow of the Big Bang. The distribution of dark matter in the early universe affected how matter clumped together, influencing the temperature fluctuations observed in the cosmic microwave background radiation, which scientists study to understand the universe's history and composition. The gravitational influence of dark matter helped to create the conditions necessary for the universe as we know it, leading to the formation of galaxies, galaxy clusters, and even the vast voids between them. There are several leading theories regarding the nature of dark matter. One popular hypothesis is that it is made up of weakly interacting massive particles, or WIMPs. These hypothetical particles would only interact through gravity and possibly through the weak nuclear force, making them difficult to detect. Other candidates include axions and sterile neutrinos, each of which presents unique challenges and avenues for research. Experiments around the world are dedicated to detecting dark matter, directly or indirectly, using various methods, from particle colliders to underground detectors, all in hopes of uncovering this elusive substance. The role of dark matter, cosmic microwave background radiation, often abbreviated as CMB, is one of the most fascinating remnants of the Big Bang, which occurred about 13.8 billion years ago. This radiation fills the universe and provides a snapshot of the infant universe, just 3.80000 years after its explosive birth. At this time, the universe had cooled enough for protons and electrons to combine and form hydrogen atoms, allowing light to travel freely through space for the first time. Before this moment, the universe was a hot, dense plasma of particles, making it opaque. As the light was released, it has been traveling through the universe ever since, and today we can detect it as a faint glow permeating the cosmos, with its temperature measured at about 2.7 Kelvin, which is just above absolute zero. The CMB is not just a relic from the past. It holds key information about the early universe's conditions, the rate of its expansion, and the formation of cosmic structures. It is remarkable that this radiation is remarkably uniform, with slight fluctuations in temperature that reflect the density variations of matter in the early universe. These fluctuations are crucial because they are thought to be the seeds of all the galaxies and clusters of galaxies that we see today. By studying the CMB, scientists can glean insights into the universe's composition, including the amounts of dark matter, dark energy, and ordinary matter. In 1965, Arno Penzias and Robert Wilson accidentally discovered the CMB while working with a microwave antenna at Bell Labs. They initially thought the persistent noise they were detecting was due to equipment malfunction or interference from pigeons, but eventually they realized it was actually the afterglow of the Big Bang. Their groundbreaking discovery provided strong evidence for the Big Bang theory, earning them the Nobel Prize in Physics in 1978. Further studies of the CMB have been conducted using satellites like the Wilkinson Microwave Anisotropy, the Planck satellites, which have mapped the radiation with incredible precision. These missions have revealed detailed images of the CMB, showing the minute temperature fluctuations across the sky, which are essential for understanding the universe's evolution. The data collected helps cosmologists refine their models of the universe, leading to a better understanding of its age, size, and overall structure. The CMB also serves as a powerful tool for testing theories of inflation, a rapid expansion that supposedly occurred just after the Big Bang. The inflationary The evolution of stars and planets is a fascinating journey through time. Beginning with the birth of stars in massive clouds of gas and dust, known as nebulae. These clouds, composed mainly of hydrogen and helium, collapse under their own gravity, forming dense regions that eventually ignite nuclear fusion in their cores, creating the energy that makes stars shine. As a star begins its life, it enters the main sequence phase, where it spends most of its life fusing hydrogen into helium, a process that can last billions of years, depending on the star's mass. Massive stars, those much larger than our Sun, evolve more quickly, burning through their hydrogen fuel at a rapid pace. Once they exhaust their hydrogen, they enter the next phase of evolution, expanding into red giants, where helium fusion begins, creating heavier elements such as carbon and oxygen. This is where things get particularly interesting, as the fate of a star is closely tied to its mass. Low to medium mass stars, like our Sun, will eventually shed their outer layers, creating beautiful planetary nebulae, while their cores collapse into white dwarfs, hot remnants that will cool and fade over billions of years. On the other hand, massive stars undergo a much more dramatic end. After exhausting their nuclear fuel, they can no longer support themselves against gravity and may explode in a supernova, a cataclysmic event that disperses elements into space, enriching the interstellar medium with materials necessary for the formation of new stars and planets. As these explosions occur, they can trigger the formation of new nebulae, leading to the birth of new stars and, potentially, a new solar system. The remnants of supernovae can also collapse to form neutron stars or black holes, some of the densest objects in the universe. Now, the planets, which are formed from the residual gas and dust surrounding a newly formed star, follow a different evolutionary path. In a protoplanetary disk, tiny particles collide and stick together, creating larger bodies called planetesimals. Over time, these planetesimals accumulate more material, forming planets. The process varies based on the distance from the star. Close to the star, where it is hotter, rocky planets like Earth and Mars can form, while farther out, where it is cooler, gas giants like Jupiter and Saturn develop, gathering thick atmospheres of hydrogen and helium. The diversity of planets we see today is a result of these complex interactions. The fate of Earth in cosmic terms is a fascinating topic that invites us to think about our planet's future on a grand scale. To understand this, we first need to consider the life cycle of stars, as our Sun is a star, and its evolution will play a crucial role in Earth's destiny. In about 5 billion years, our Sun will exhaust its nuclear fuel and expand into a red giant, engulfing the inner planets, including Earth, or at the very least, stripping away its atmosphere and rendering it uninhabitable. This transformation will mark a significant turning point in the Earth's story, as the heat from the expanding Sun will lead to catastrophic changes on our planet's surface, boiling oceans and scorching land, making life as we know it impossible. However, the story of Earth does not end there. Once the Sun sheds its outer layers, it will leave behind a hot core, known as a white dwarf. This remnant will gradually cool over billions of years, but by then Earth, if it still exists in some form, will be a lifeless rock, orbiting an increasingly cold star. From a cosmic perspective, this is just one chapter in a much larger narrative. The universe is vast and ever-changing, with galaxies colliding, stars being born and dying, and planets forming and disintegrating. In our Milky Way galaxy alone, countless stars will have their own life cycles, leading to a cosmic dance of creation and destruction. Moreover, looking beyond our own solar system, we find that the fate of Earth is also tied to the future of the Milky Way. potentially for galaxy is on a completely different cosmic landscape, influenced by the forces of this galactic collision, internally leading to the merging of stars and even new star formation. While Earth may be long gone by then, the remnants of our solar system could find themselves in a completely different cosmic landscape, potentially leading to the merging of stars and even new star formation, organized by the galaxy, influenced by the forces of this galactic collision. On an even grander scale, the fate of Earth is intertwined with the ultimate fate of the universe itself. There are several theories about how the universe will end, such as the Big Freeze, where galaxies drift apart, stars burn out, and the universe reaches a state of maximum entropy, making it cold and dark. Alternatively, scenarios like the Big Crunch suggest that the universe could eventually stop expanding and start contracting, leading to a collapse back into a singularity. Then, the emergence of life in the universe is a fascinating topic, one that has intrigued scientists, philosophers, and curious minds for centuries. Scientists believe that life, as we understand it, emerged on Earth around 3.5 to 4 billion years ago. But the question of how and if life exists elsewhere in the universe remains a hotly debated subject. The conditions required for life, such as liquid water, a stable temperature range, and a source of energy, have led researchers to explore various environments beyond Earth. For instance, the discovery of extremophiles, organisms that thrive in extreme conditions, suggests that life could potentially exist in places previously thought to be inhospitable, like the icy moons of Jupiter and Saturn, such as Europa and Enceladus. These moons have subsurface oceans beneath their icy crusts, creating conditions that might support microbial life. Moreover, the search for exoplanets, planets orbiting stars outside our solar system, has intensified with the advent of advanced telescopes and observation techniques. Astronomers have identified thousands of exoplanets, some of which lie within their star's habitable zone, where conditions could be just right for liquid water to exist. The Kepler Space Telescope, for example, has played a crucial role in this discovery, revealing a diverse array of planetary systems. One notable finding is that many of these exoplanets are rocky, similar to Earth, which raises the possibility that they could host life. Astrobiology, the study of the potential for life beyond Earth, has become a multidisciplinary field, combining elements of biology, chemistry, astronomy, and geology. Researchers are investigating the chemical building blocks of life, such as amino acids and nucleotides, which have been found in meteorites and in the atmospheres of distant planets. The presence of these organic molecules suggests that the ingredients for life may be widespread throughout the universe, leading to the intriguing possibility that life could emerge independently on different worlds. Further, the concept of panspermia posits that life, or at least the building blocks of life, could be distributed throughout the universe via comets, asteroids, or meteoroids. This theory suggests that life might not have originated on Earth, but could have been delivered here from elsewhere, in the cosmos. Experiments simulating space conditions have shown that microorganisms can survive the harsh environment of space, lending some credence to this idea. The search for extraterrestrial intelligence, or SETI, is supernovae, are some of the most powerful and energetic events in the universe, marking the explosive deaths of massive stars, and they play a crucial role in cosmic evolution. When a massive star exhausts its nuclear fuel, it can no longer support itself against the force of gravity, leading to a catastrophic collapse. This collapse results in an explosive outflow of energy and materials, which disperses elements into the surrounding space. The energy released during a supernova can briefly outshine entire galaxies, providing astronomers with a unique opportunity to study these colossal events from vast distances. One of the most significant contributions of supernovae to cosmic evolution is their role in nucleosynthesis, the process of creating new elements. During the explosion, Supernovae generate and spread heavy elements such as iron, gold, and uranium into the interstellar medium. These elements are crucial for the formation of new stars, planets, and ultimately, life as we know it. Without supernovae, the universe would lack many of the heavier elements necessary for complex chemistry, making the emergence of life improbable. Furthermore, the materials expelled by supernovae contribute to the recycling of matter in the universe. As gas and dust from past stellar generations accumulate, they form molecular clouds, which can collapse under gravity to form new stars. This cycle of star formation and destruction is a fundamental aspect of galactic evolution, influencing the structure and composition of galaxies over billions of years. Supernovae also have a significant impact on the dynamics of galaxies. The shock waves produced by these explosions can trigger the formation of new stars, compressing nearby gas and dust. This can lead to bursts of star formation in regions of a galaxy that were previously quiet. Additionally, supernovae can disrupt existing star systems and influence the motion of stars, contributing to the overall evolution of a galaxy's structure. In terms of cosmic distances, supernovae serve as important candles in astronomy. Type Ia supernovae, for instance, have a consistent peak brightness, which allows astronomers to measure the distance to their host galaxies with great accuracy. This has been fundamental in understanding the expansion of the universe and has provided evidence for the existence of dark energy, a mysterious force that is driving the acceleration of that expansion. The study of supernovae also sheds light on the life cycles of stars, enhancing our understanding of stellar evolution. By observing the light curves and spectra of supernovae, astronomers can infer the properties. Cosmic strings are fascinating. Theoretical objects that arise in the field of cosmology and theoretical physics, often associated with the early universe, shortly after the Big Bang. These strings are not like the ones we use in daily life. Instead, they are one-dimensional topological defects that can stretch across vast distances. Even across the observable universe, they are thought to be remnants from phase transitions in the early universe, similar to how defects can occur when water freezes into ice. Researchers believe that cosmic strings could have formed during the symmetry-breaking phase transitions that occurred as the universe cooled, leading to the formation of different forces and particles. One of the most intriguing aspects of cosmic strings is their potential impact on the fabric of space-time itself. According to general relativity, massive objects can warp space-time, and cosmic strings are predicted to have an extreme gravitational effect due to their immense density, which is theorized to be comparable to that of a black hole. This means that if cosmic strings exist, they could create gravitational fields that are strong enough to bend the path of light, leading to what is known as gravitational lensing. This phenomenon could allow us to observe cosmic strings indirectly, as they might distort the appearance of distant galaxies and other celestial objects. Moreover, cosmic strings might also play a role in the formation of large-scale structures in the universe. When they stretch across vast distances, they could influence the distribution of matter, causing clumps of matter to form along their lengths. This could help explain the observed patterns of galaxy formation and distribution that we see today. In this context, cosmic strings could be seen as a sort of cosmic scaffolding, shaping the universe as it evolves. Another interesting aspect of cosmic strings is their relationship with other theoretical concepts, such as monopoles and vortex lines. Monopoles are hypothetical particles that carry a single magnetic charge, while vortex lines are related to the behavior of superfluids. The interplay between these concepts and cosmic strings points to a deeper understanding of the fundamental forces of nature and the conditions of the early universe. Astrophysicists have been actively searching for evidence of cosmic strings using a variety of methods, including the analysis of cosmic microwave background radiation and gravitational wave detectors. While no direct evidence has been found yet, the implications of their existence could be profound, potentially providing insights into the very nature of the universe, the forces that govern it, and the conditions that prevailed during its infancy. In summary, cosmic strings are not just a theoretical curiosity. The collapse of the universe into a singular point, often referred to as the Big Crunch, is a fascinating concept in cosmology, suggesting a possible end to the universe's expansion. In the early 20th century, scientists like Alexander Friedmann and Georges Lemaitre proposed that the universe was expanding, a notion that was later supported by Edwin Hubble's observations of distant galaxies moving away from us. However, if the density of the universe is sufficient, the gravitational attraction of all matter could eventually overcome this expansion, leading to a scenario where the universe begins to contract. In this scenario, galaxies would drift closer together, stars would collide, and the temperature would rise dramatically as everything draws nearer. This process would continue until all matter in the universe comes together into an incredibly dense state, potentially forming a singularity, where the laws of physics as we know them break down. The idea of the universe collapsing into a singular point raises intriguing questions about the fabric of space and time. Theories suggest that, at this point, space-time could become infinitely curved, leading to conditions where our current understanding of physics, particularly the theories of general relativity and quantum mechanics, might not apply. This singularity could mark the end of the universe as we know it. But some scientists propose that it could also lead to a new beginning, possibly giving rise to a new Big Bang, an event that would start the cycle all over again. Various models of the universe's fate exist, including the Big Freeze, where the universe continues to expand forever, and the Big Rip, where dark energy causes the universe to tear itself apart. However, the Big Crunch presents a more cyclical view of cosmic evolution, suggesting that the universe could undergo infinite expansions and contractions. This leads to philosophical questions about the nature of existence and whether the universe is destined for an eternal cycle or a singular end. Interestingly, the current understanding of dark energy, which drives the accelerated expansion of the universe, challenges the idea of a Big Crunch. As observations indicate that dark energy's influence appears to be constant, it seems less likely that the universe will reverse its expansion anytime soon. Nevertheless, the concept of collapse into a singular point continues to be a subject of intrigue and study, sparking discussions about the ultimate fate of our cosmos and the fundamental laws governing it. Scientists are continually exploring these themes, using advanced telescopes and simulations to gather more data and refine their models, as they seek to understand the mysteries that time travel has fascinated people for generations. And various theories have emerged, each with its own unique perspective. Some scientists suggest that time travel could be possible through concepts like wormholes, which are theoretical passages through space-time that could create shortcuts between different points in time and space. According to Einstein's theory of general relativity, these wormholes could exist, but we currently lack the technology to create or navigate them. Another popular theory is based on the concept of time dilation, which occurs when an object moves at speeds close to the speed of light, causing time to pass differently for it compared to an observer at rest. This effect, predicted by Einstein, has been confirmed through experiments with atomic clocks flying on airplanes, which show that time indeed runs slower for them compared to clocks on the ground. There's also the intriguing idea of parallel universes, which suggests that every decision we make could create a branching timeline, leading to countless alternate realities. This means that if time travel were possible, one could potentially visit not just the past or future of our universe, but also alternate versions of it. This theory raises fascinating questions about the nature of reality and our choices. However, the idea of changing the past brings us to the grandfather paradox, which poses a logical dilemma. If you were to travel back in time and prevent your grandfather from meeting your grandmother, would you still exist? This paradox highlights the complexity of time travel and the potential consequences of altering past events. As for the endings of the universe, scientists have proposed several theories based on current observations and cosmological models. One of the most discussed scenarios is the Big Freeze, which suggests that as the universe continues to expand, it will eventually reach a state where stars burn out, galaxies drift apart, and the universe grows dark and cold. This scenario is supported by the discovery of dark energy, which is driving the accelerated expansion of the universe. Another theory is the Big Crunch, which posits that the gravitational forces of matter could eventually halt this expansion and reverse it, leading to a collapse into a singularity, potentially followed by a new Big Bang. Then there's the Big Rip hypothesis, which suggests that if dark energy continues to increase in strength, it could tear apart galaxies, stars, planets, and even atoms themselves, leading to a dramatic end where everything is ripped apart. Each of these theories offers a unique perspective on the future of the universe, and as our understanding of physics deepens, we may find new insights into these Bahal. The role of black holes in information loss is a captivating topic that intertwines the realms of physics, quantum mechanics, and the very nature of reality itself. At the heart of this discussion is a fundamental question: can information, once it falls into a black hole, ever be recovered? According to classical physics, when an object crosses the event horizon of a black hole, it is lost to the universe, seemingly taking all the information about its state with it. This idea, however, raises significant concerns that challenge our understanding of physics, particularly the principles of quantum mechanics, which suggest that information cannot be destroyed. This paradox became widely known through debates involving renowned physicists, such as Stephen Hawking, who proposed that black holes could emit radiation, now famously referred to as Hawking radiation, which implies that black holes might eventually evaporate. If they do evaporate, questions arise about what happens to the information that was swallowed by the black hole. Hawking's initial stance suggested that information could be irretrievably lost, leading to what is known as the information paradox. In contrast, other physicists argue that the information could somehow be preserved, perhaps encoded in the Hawking radiation itself, or stored in the black hole's event horizon, a concept known as the holographic principle. This principle posits that all the information contained within a volume of space can be represented as a theory that lives on the boundary of that space. The debate over the fate of information in black holes has sparked numerous theories and ideas, including the notion that black holes might function as giant archives, storing information in a scrambled state that could, in theory, be deciphered in some way. Additionally, researchers have explored the concept of black hole complementarity, which posits that observers falling into a black hole and those remaining outside experience different realities. Yet both perspectives are valid. This leads to a fascinating implication. The information could be preserved in a way that is not accessible to any single observer, which challenges our understanding of observer-dependent reality. Moreover, advancements in quantum gravity and string theory may provide insights into this dilemma, offering potential frameworks that could reconcile the principles of quantum mechanics with the peculiarities of black holes. The quest to understand the role of black holes in information loss is ongoing, drawing in researchers from various fields and prompting new ideas about the fundamental nature of space, time, and information itself. As scientists continue to investigate these cosmic mysteries, they not only challenge our understanding of black holes, but also push gravity waves, which are different from gravitational waves, play a significant role in our understanding of various physical phenomena. These waves are essentially oscillations in the fabric of space and time, caused by the movement of mass, such as ocean waves shifting due to the gravitational pull of the moon, or atmospheric waves that occur as air moves over mountains. The influence of gravity waves can be observed in many areas, including meteorology, astrophysics, and even in the study of climate change. For example, in the atmosphere, gravity waves can be created when air flows over mountains, leading to changes in wind patterns and local weather conditions. These waves can propagate long distances, affecting weather systems far from their source, which is why they are crucial for meteorologists to understand, as they help in predicting storms and other weather events more accurately. In the ocean, gravity waves are responsible for creating surface waves, which are what, actually, we typically think of when we picture the sea. These waves are driven by the gravitational forces exerted by the moon and the sun, and their influence can be seen in tidal movements and ocean currents. The study of these waves is vital for navigation, coastal management, and understanding marine ecosystems, as they affect everything from sediment transport to the behavior of marine life. Additionally, gravity waves also play a role in climate models, as they can influence heat distribution in the atmosphere and oceans, thus impacting global climate patterns. In astrophysics, gravity waves can help us understand the dynamics of celestial bodies, such as stars and galaxies. When massive objects like black holes or neutron stars collide, they can produce gravitational waves, ripples in space-time that scientists have only recently begun to detect. Observatories like LIGO have opened a new window into the universe, allowing researchers to study these events and gain insights into the nature of gravity itself. The influence of gravity waves extends beyond simple movement. It can affect the structure and evolution of the universe, shedding light on phenomena that were once thought to be purely theoretical. Moreover, the study of gravity waves is not limited to just theoretical physics. It has practical applications as well. For instance, understanding the effects of gravity waves can enhance our ability to model weather patterns, improving agricultural planning and disaster preparedness. This knowledge can help predict severe weather events, giving communities more time to prepare for potential impacts. In addition, the insights gained from studying gravity waves can lead to advancements in technology, such as improving satellite communications, as these waves can affect signal propagation. The ongoing research, cosmic events, and catastrophes are fascinating phenomena that have captivated human imagination for centuries. One of the most significant and awe-inspiring cosmic events is a supernova, which occurs when a massive star exhausts its nuclear fuel and collapses under its own gravity, leading to an enormous explosion that can outshine entire galaxies for a brief period. These explosions not only create stunning celestial displays, but also scatter heavy elements throughout the universe, contributing to the formation of new stars and planets. Another intriguing event is a gamma-ray burst, a highly energetic explosion observed in distant galaxies, which is thought to occur when massive stars collapse into black holes or when neutron stars collide. These bursts release more energy in a few seconds than the sun will emit in its entire lifetime, making them the most powerful explosions known in the universe. On a more catastrophic scale, we have asteroid impacts, which have played a crucial role in shaping the history of our planet. For instance, the impact of a large asteroid around 66 million years ago is widely believed to have contributed to the mass extinction event that wiped out the dinosaurs. This event, known as the Cretaceous-Paleogene extinction event, serves as a reminder of how cosmic events can have profound effects on life on Earth. Scientists continually monitor near-Earth objects, as even a relatively small asteroid could cause significant damage if it were to collide with our planet. Moreover, the phenomenon of cosmic rays, which are high-energy particles originating from outer space, presents another intriguing aspect of cosmic events. These particles can travel at nearly the speed of light and are thought to originate from supernovae and other high-energy astrophysical processes. When cosmic rays enter the Earth's atmosphere, they can create a cascade of secondary particles, some of which can even reach the surface. While most cosmic rays are harmless, they pose risks to astronauts in space, and their effects on long-term space travel are a topic of ongoing research. Black holes, which are regions of space where gravity is so strong that nothing, not even light, can escape, are another compelling subject of study. Supermassive black holes found at the centers of most galaxies, including our Milky Way, can influence the motion of stars and gas in their vicinity. The phenomenon of spaghettification, which occurs when an object gets too close to a black hole and is stretched by gravitational forces, paints a vivid picture of the extreme conditions that exist in these cosmic giants. Finally, let's not forget about the artificial intelligence, or AI, is becoming an increasingly important part of our lives, and its role in future scenarios is both exciting and complex. And as we look ahead, AI is expected to transform industries, improve our daily lives, and even shape the way we interact with the world. In healthcare, for instance, AI algorithms are being developed to analyze medical data, predict patient outcomes, and assist in diagnosing diseases earlier than traditional methods allow, which could lead to significant improvements in treatment and patient care. In the realm of transportation, self-driving cars are no longer just a concept from science fiction. They are being tested on our roads, promising to reduce accidents caused by human error and to optimize traffic flow in crowded cities, potentially leading to less congestion and cleaner air. Education, too, is set to be revolutionized by AI technology, offering personalized learning experiences for students. With AI systems that can adapt to individual learning styles and paces, teachers will be able to focus more on facilitating learning rather than delivering one-size-fits-all lectures, which could lead to better educational outcomes for many students. Moreover, AI is becoming a key player in the field of climate change, as researchers are utilizing machine learning to analyze vast amounts of data, helping us understand complex environmental issues, predict climate patterns, and develop strategies for sustainability. In the creative industries, AI is already making waves, with algorithms capable of composing music, creating visual art, and even writing stories. These advancements challenge our traditional notions of creativity and authorship, prompting questions about the role of human artists in a world where machines can create. Furthermore, in the business sector, AI-driven analytics are helping companies make more informed decisions by predicting market trends and consumer behavior, thus allowing businesses to stay competitive in an ever-evolving marketplace. However, the integration of AI into various aspects of society also raises important ethical considerations. Concerns about privacy, security, and the potential for job displacement due to automation are at the forefront of discussions about AI's future. As machines take over more tasks, the workforce may need to adapt, necessitating a shift in skill sets and job training programs to prepare individuals for new roles that AI cannot easily replicate, such as those involving emotional intelligence, complex problem solving, and interpersonal communication. Regulation is another crucial aspect of AI's future, as governments and organizations strive to establish guidelines that ensure AI technologies are developed and deployed responsibly. This includes addressing biases in AI algorithms, ensuring transparency in AI decision-making processes, and protecting individuals. As we delve into the vastness of space, it's fascinating to consider how our actions on Earth may influence the future of the cosmos. Human activity, primarily through technological advancements and environmental impacts, has created ripples that could eventually extend beyond our planet. For instance, the increasing emissions of greenhouse gases not only affect our atmosphere, but, in the long term, may alter the characteristics of the Earth itself, influencing its gravitational pull and, potentially, its orbit. This could have far-reaching consequences, not just for us, but for the solar system as a whole, as even slight changes in Earth's position could impact the delicate balance that sustains life. Moreover, the exploration of space, driven by a combination of scientific curiosity and commercial interests, has led to the development of numerous satellites, space stations, and even plans for colonization of other planets. This expansion into the cosmos raises questions about space debris, which is a growing concern. As we launch more and more objects into orbit, the potential for collisions increases, which could create even more debris, further complicating our relationship with space. This debris could endanger future missions, and it might even affect the natural orbits of celestial bodies, creating a chaotic environment in what should be the serene expanse of space. Additionally, the search for extraterrestrial life has intensified, with missions to Mars, the study of icy moons like Europa, and the exploration of exoplanets in habitable zones. Our attempts to communicate with potential alien civilizations through projects like SETI pose ethical questions about the impact of our presence in the cosmos. If we were to make contact, how would that alter our trajectory? And what responsibilities would we have regarding the preservation of these other worlds and their potential inhabitants? Furthermore, as we mine asteroids for resources and seek to utilize the materials available in space, we must consider the implications of those actions. Extracting resources from celestial bodies could lead to a new era of space economy, but it also poses risks of exploitation and environmental destruction, even in the vacuum of space. The long-term consequences of such activities could reshape not just our solar system, but the entire galaxy, potentially leading to conflicts over resources or the preservation of cosmic heritage. On a more philosophical level, our human experiences and cultural narratives about space can influence how we perceive our place in the universe. The stories we tell about our endeavors in space exploration, whether they be about triumphs or failures, shape public opinion and can inspire future generations to explore. Theoretical physics, one of the most fascinating areas of study, revolves around predictions about the universe, which often challenge our understanding of reality. Theoretical physicists use complex mathematics and innovative concepts to explore fundamental questions about space, time, and matter. One prominent theory is string theory, which suggests that the basic building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings exist in multiple dimensions, beyond the familiar three of space and one of time, leading to the prediction of additional dimensions that we cannot directly observe. This idea, while still unproven, offers intriguing possibilities for unifying the forces of nature, including gravity, electromagnetism, and the nuclear forces, into a single framework. Another significant aspect of theoretical physics involves the study of black holes, which are regions of space where gravity is so strong that nothing, not even light, can escape. Theoretical predictions about black holes have led to revolutionary ideas such as Hawking radiation, proposed by physicist Stephen Hawking. This concept suggests that black holes can emit radiation due to quantum effects near their event horizons. If true, this leads to the fascinating possibility that black holes could eventually evaporate over incredibly long timescales, reshaping our understanding of their life cycle and the fate of matter. Moreover, cosmology, study of the universe as a whole, includes predictions about its expansion. The discovery of the universe's accelerating expansion, attributed to dark energy, has puzzled scientists. Dark energy is thought to make up about 70% of the universe, yet its nature remains one of the biggest mysteries in physics. Theoretical physicists are working to understand what dark energy is, how it affects the universe, and whether it will lead to different possible futures for the cosmos, such as the Big Freeze, where galaxies drift apart, or the potential for a big crunch, where the universe could eventually collapse back on itself. In addition to these concepts, theoretical physics also delves into the realm of multiverse theory, which posits that our universe may be just one of many, each with different physical laws and constants. This idea emerges from the inflationary model of the universe, which suggests that during its early moments, the universe underwent rapid expansion, potentially leading to the creation of multiple, disconnected regions of space-time. The implications of a multiverse are profound, raising questions about the nature of reality and the very fabric of existence. Each of these theories, while in the vast and intricate tapestry of the universe, the role of probability and chance becomes a fascinating lens through which we can examine cosmic endings. When we contemplate the fate of the universe, we often consider different scenarios based on scientific theories. But the underlying factors of probability and chance play a crucial role in shaping those outcomes. For instance, one of the prevailing theories regarding the ultimate fate of the universe is the Big Freeze, or heat death, which suggests that as the universe expands, it will eventually reach a state of maximum entropy, where stars burn out, galaxies drift apart, and the cosmos becomes a cold, dark expanse. Scientists use statistical models to estimate these probabilities, but there is always an element of uncertainty, as new discoveries can change our understanding of the universe's composition. This uncertainty introduces an element of chance into the fate of the cosmos, making the outcomes less deterministic and more reliant on factors that we may not fully comprehend yet. Additionally, the concept of cosmic events such as supernovae or gamma-ray bursts also illustrates the interplay of probability and chance. These cataclysmic occurrences can dramatically affect their surrounding environments, potentially leading to the creation of black holes. The likelihood of a supernova occurring in a given star system is governed by various factors, including the mass of the star and its life cycle, which can be predicted using statistical models. However, the exact timing and consequences of such events remain unpredictable, highlighting the chaotic nature of the universe. In a more philosophical sense, the role of probability in cosmic endings also invites us to consider the multiverse theory, which posits that our universe might be just one of many, each with its own set of physical laws and constants. If this theory holds true, the probability of different cosmic endings could vary dramatically across different universes. Some might experience rapid expansion, while others might collapse in on themselves, and the vast range of possible outcomes emphasizes the randomness and complexity of existence. Furthermore, human life on Earth and our understanding of the universe introduces another layer of chance to the discussion. The ethical implications of universe endings, a topic that stretches the boundaries of philosophy, science, and morality, invite intriguing discussions. When we consider the end of the universe, it raises important questions about existence, purpose, and the fate of all living beings. For instance, if we think about potential scenarios like the Big Freeze, the Big Crunch, or a heat death, we must ask ourselves what these endings mean for our understanding of life and our responsibilities as conscious beings. How should we approach the idea of cosmic finality, knowing that everything we cherish might one day cease to exist? This leads to reflections on value and meaning as we grapple with the notion that our actions, however significant, may ultimately be rendered meaningless in an indifferent universe. Moreover, contemplating the end of the universe prompts us to examine the ethical responsibilities we have towards our planet and each other. If we accept that all things have an end, does it not compel us to treat our environment with more respect? The potential extinction of humanity, or even the death of the stars, challenges us to act with a greater sense of urgency and care, recognizing that our time is finite. This also leads to questions about how we should prioritize resources as we face pressing issues like climate change, poverty, and inequality. Should we invest in technologies that might allow us to escape our planet, or should we focus on ensuring a better life for those who are here now, knowing that the universe itself has an expiration date? Furthermore, exploring the ethical implications of universe endings can also touch upon the concept of legacy. What kind of legacy do we want to leave behind, knowing that the universe will eventually fade away? This thought can inspire people to think deeply about their actions, their contributions to society, and how they wish to be remembered. It raises the question of whether we should strive for immortality, either through our achievements or through advancements in science, or if we should accept mortality as a natural part of existence. On a more speculative note, if we consider the possibility of multiverses, where our universe is just one of many, what ethical considerations arise from the existence of alternate realities? Does this mean we have multiple chances to get things right? Or does it complicate our understanding of morality, as actions in one universe may not have the same implications in another? This scenario could lead to discussions about the value of life across different dimensions and the responsibilities we might have towards other beings that could exist in these parallel universes. Philosophical perspectives on cosmic fate delve into the intricate relationship between human existence, the universe, and the concept of destiny. Throughout history, various philosophical schools have attempted to unravel the mysteries of why we are here and whether our lives are governed by predetermined paths or shaped by our choices. Ancient Greek philosophers like Heraclitus believed in a universe characterized by constant change, where the only constant is change itself, suggesting that while there may be a cosmic order, individual fate is not fixed, but rather fluid and influenced by our actions. In contrast, the Stoics posited a more deterministic view of fate, arguing that everything happens according to a divine reason, or logos, and that human beings should strive to accept their fate with grace, focusing on what they can control, rather than lamenting what they cannot change. Moving into Eastern philosophies, particularly in Buddhism, the concept of fate is closely tied to karma. This perspective suggests that our current circumstances are a result of our past actions, and while we may not have control over our initial conditions, we certainly have the power to influence our future through our deeds in the present. This introduces a dynamic interplay between fate and free will, where individuals are seen as active participants in their destiny, creating a tapestry of interconnected lives and experiences. In more contemporary discussions, existentialist philosophers like Jean-Paul Sartre challenge the idea of cosmic fate altogether, asserting that existence precedes essence, This means that human beings are not born with a predetermined purpose, rather, they create their own essence through choices and actions. Sartre's view emphasizes personal responsibility, suggesting that we are the architects of our own futures, casting aside the notion of a cosmic plan. On the other hand, the philosophy of fatalism presents a different angle, positing that events are predetermined and inevitable, regardless of human effort. This raises intriguing questions about moral responsibility and the nature of human agency. If everything is fated to happen, can we truly be held accountable for our choices? The implications of such a viewpoint can be both liberating and paralyzing, as it challenges the very essence of free will that many cultures hold dear. Moreover, in the realm of metaphysics, questions arise about the nature of time and existence. Some philosophers, like David Lewis, have explored the concept of modal realism, which suggests that all possible worlds are as real as the actual world we inhabit. This leads to fascinating discussions about alternative outcomes and the many paths that could have been taken, further complicating cultural responses to the end of the universe. Abound in various forms of art, literature, and philosophy, reflecting humanity's deep curiosity, fear, and hope regarding our ultimate fate. Many cultures, through myths and legends, have grappled with the concept of the cosmos's end, often depicting it in grand narratives that explore themes of rebirth, transformation, and cyclical creation. For instance, Hindu cosmology describes a cyclical universe, where creation and destruction occur in endless cycles, embodied in the dance of Shiva, symbolizing the perpetual flow of existence. This notion provides a fascinating perspective, as it suggests that the end is not a finality, but rather a transition to a new beginning, allowing for infinite possibilities. In literature, the idea of the universe's end has sparked the imagination of countless authors. Works such as The Road by Cormac McCarthy, which depicts a post-apocalyptic world, invite readers to ponder the fragility of civilization and the resilience of the human spirit. Similarly, Isaac Asimov's The Last Question confronts the concept of entropy and the eventual heat death of the universe, presenting a thought-provoking dialogue on humanity's quest for immortality and understanding. These narratives not only entertain, but also challenge us to reflect on our place in the universe and the legacies we leave behind. Philosophically, the end of the universe prompts profound questions about existence, purpose, and meaning. Existentialist thinkers, such as Jean-Paul Sartre and Albert Camus, argue that the apparent absurdity of life in the face of an indifferent universe can lead to a more authentic existence. They suggest that instead of succumbing to despair, individuals can create their own meaning, embracing the freedom that comes with acknowledging our mortality. This perspective can offer solace, reminding us that our experiences, relationships, and passions are significant, even in the face of an inevitable end. In contemporary culture, the end of the universe has found a place in popular media, from blockbuster films to television series, often portrayed through apocalyptic scenarios. Movies like Interstellar and Arrival explore themes of time, space, and human connection, while addressing the scientific theories surrounding the universe's fate. These films not only captivate audiences with stunning visuals and compelling stories, but also serve as a bridge between complex scientific ideas and everyday understanding, sparking curiosity about astrophysics and cosmology. Art, too, has responded to the theme of cosmic endings, with artists using religion. Religion has long been a lens through which humanity seeks to understand the mysteries of existence, including the concept of cosmic endings. Many religious traditions offer narratives about the universe's beginning, its current state, and its ultimate fate, serving not only as spiritual guidance, but also as frameworks for interpreting the cosmos. For instance, in Christianity, The Book of Revelation describes an apocalyptic vision where the world faces a final judgment, leading to the creation of a new heaven and new earth, while in Hinduism, the cycle of creation and destruction, known as samsara, illustrates an endless loop of cosmic endings and beginnings, underscoring a belief in rebirth and renewal. Meanwhile, Buddhism presents a view that emphasizes impermanence, suggesting that all things, including the universe itself, are transient and subject to change. In contrast, many indigenous belief systems incorporate a sense of stewardship over the earth, reflecting a deep connection with nature, and they often view cosmic endings as part of a larger cyclical process rather than definitive conclusions. Moreover, the role of religion in understanding cosmic endings extends beyond mere narratives. It also influences cultural attitudes and ethical considerations regarding our relationship with the universe. For example, the belief in an impending apocalypse can lead to a sense of urgency about environmental issues, motivating communities to take action to protect the planet. Reflecting the idea that the fate of the earth is intertwined with spiritual well-being. Similarly, eschatological beliefs can inspire hope, encouraging individuals to find meaning in life's struggles and uncertainties, as they view their existence as part of a larger divine plan. As scientific discoveries advance, some religious groups engage in dialogues between faith and science, exploring concepts like the Big Bang, cosmic evolution, and even theories about the eventual heat death of the universe. These discussions can lead to a richer understanding of existence, merging spiritual insights with empirical observations. For instance, some theologians argue that the scientific narrative of the universe's expansion and cooling aligns with their beliefs about a divine creator who initiated and continues to influence cosmic processes. In this interplay of ideas, religion acts as a bridge that connects human experience with the vastness of the cosmos, igniting curiosity and wonder about our place in it. The questions of why we exist, the purpose of life, and what might happen at the end of everything remain deeply ingrained in the human psyche, prompting explorations that span both spiritual and scientific realms. Ultimately, the role of religion in understanding cosmic endings is multifaceted, shaping speculative fiction, a genre that encompasses a wide range of imaginative storytelling, often delves into the concept of universe endings, exploring how different worlds might meet their ultimate fates, whether through cosmic events, societal collapse, or existential threats. In this genre, authors like Isaac Asimov, Arthur C. Clarke, and Ursula K. Le Guin have created rich narratives that not only entertain but also provoke thought about the future of humanity and the universe. For instance, Asimov's Foundation series presents a future where the galactic empire faces inevitable decline, leading to the exploration of psychohistory, a fictional science that attempts to predict the future of large populations, raising questions about determinism and free will. Meanwhile, Clarke's Rendezvous with Rama introduces readers to a giant alien spacecraft entering the solar system, highlighting humanity's place in the cosmos and the potential for both awe and dread in the face of the unknown. The endings of universes in speculative fiction can take many forms, from apocalyptic scenarios where human civilization crumbles under the weight of its own advancements, as seen in novels like The Road by Cormac McCarthy, which portrays a bleak, post-apocalyptic landscape, to more optimistic or ambiguous conclusions, like in The Dispossessed by Le Guin, where the protagonist seeks to bridge the divide between two vastly different societies, ultimately questioning the nature of utopia and dystopia. Furthermore, the idea of multiverses, which suggests the existence of multiple, possibly infinite universes, offers a fascinating lens through which to consider endings, as explored in works like the Dark Tower series by Stephen King, where different worlds interact and influence each other, leaving readers to ponder the endless possibilities and outcomes that could arise from each decision made in various universes. Additionally, speculative fiction often draws on scientific theories to explore the fate of the universe itself, such as the Big Crunch, where the universe might eventually stop expanding and begin contracting, leading to a singularity, or the Big Freeze, where it continues to expand until stars burn out and galaxies drift apart. These concepts inspire narratives that delve into the human experience in the face of such grand scales, as seen in works like The Three-Body Problem by Liu Cixin, which explores the idea of first contact with an alien civilization and the existential threats that arise from it. In this way, speculative fiction serves not only as a form of escapism, but also as a medium for cosmic catastrophes. Those massive and often unpredictable events occurring in the universe have the potential to significantly impact life on Earth, leading many to ponder human survival in the face of such monumental forces. One of the most well-known dangers is the threat posed by asteroids and comets, which throughout history have collided with our planet, with the most famous example being the asteroid that likely caused the extinction of the dinosaurs around 66 million years ago. This event, known as the Cretaceous-Paleogene extinction event, serves as a reminder of how a single cosmic object can drastically alter the course of life on Earth. Scientists today actively track near-Earth objects, utilizing advanced telescopes and space missions to identify those that could pose a risk to our planet, with the goal of developing potential deflection strategies should a significant threat be identified. Another cosmic phenomenon that could threaten humanity is the eruption of supervolcanoes, which can occur as a result of tectonic activity influenced by forces from deep within the Earth. But the triggers for such eruptions could also be linked to cosmic events, such as the impact of a large asteroid or changes in solar radiation. A supervolcanic eruption could release enough ash and gases into the atmosphere to disrupt climate patterns, leading to what is often referred to as a volcanic winter, where temperatures drop significantly, impacting food production and ecosystems. Additionally, gamma-ray bursts, which are extremely energetic explosions observed in distant galaxies, could pose a threat if such an event were to occur near our solar system. These bursts emit intense radiation that could strip away the Earth's ozone layer, exposing life to harmful ultraviolet radiation. While the likelihood of a gamma-ray burst affecting Earth is low, the potential consequences are severe, leading scientists to consider the implications of such events on human survival. Moreover, solar flares and coronal mass ejections from the Sun can also have significant effects on Earth, particularly on our technology. A massive solar storm, similar to the Carrington event of 1859, could disrupt satellite communications, damage electrical grids, and impact everything from global positioning systems to internet connectivity. As our society becomes increasingly reliant on technology, the vulnerability to cosmic events like solar flares raises important questions about preparedness and resilience. In the realm of cosmic catastrophes, the concept of rogue planets has also captured the imagination of scientists and enthusiasts alike. A rogue planet, a planetary body that wanders through space without a star, could potentially enter the search for extraterrestrial life has captivated human imagination for centuries, sparking debates, theories, and scientific inquiries. From ancient philosophers pondering the existence of other worlds, to modern astronomers scanning the cosmos for signals. With the advent of advanced technology like powerful telescopes and space probes, our quest has accelerated, leading to exciting discoveries. For example, the discovery of exoplanets, which are planets outside our solar system, many of which lie in the so-called Goldilocks zone, where conditions might be just right for life to exist, not too hot and not too cold, allowing for the potential presence of liquid water, a key ingredient for life as we know it. The implications of finding extraterrestrial life are profound, raising questions about our place in the universe, the nature of life itself, and the potential for communication with other civilizations. Scientists are exploring various environments, such as the icy moons of Jupiter and Saturn like Europa and Enceladus, which harbor hidden oceans beneath their surfaces, potentially nurturing microbial life. Additionally, the ongoing search for radio signals through projects like SETI, the search for extraterrestrial intelligence, seeks to detect any signs of intelligent life, using radio telescopes to listen for patterns that might suggest an artificial origin, which could revolutionize our understanding of life beyond Earth. Moreover, the discovery of extremophiles, organisms that thrive in harsh conditions on Earth, further expands the possibilities of where life might exist, suggesting that if life can adapt to extreme environments here, it might also thrive in the harsh conditions of other celestial bodies, such as Mars or the sulfuric clouds of Venus. The implications of this search extend beyond scientific curiosity. They touch on philosophical, ethical, and social dimensions, as the potential discovery of extraterrestrial life could challenge our beliefs about humanity's uniqueness and our responsibilities to other forms of life, should we encounter them. Furthermore, the prospect of communicating with another civilization raises questions about the ethical implications of such interactions, including the potential for cultural exchange, technological advancement, and even conflict as we navigate the unknown territory of interstellar relations. As we venture deeper into space, missions like the Mars rovers and the James Webb Space Telescope are poised to provide unprecedented insights into the atmospheres and surface conditions of distant planets, helping us to identify biosignatures, which are indicators of life, such as specific gases in the atmosphere that could suggest biological processes. The excitement around the search for extraterrestrial life. When it comes to predicting the fate of the universe, scientists rely on a variety of scientific methods. Using advanced mathematics, observations, and theoretical models to understand how the universe might evolve over billions of years. One prominent method is through the study of cosmic background radiation, which provides insights into the early stages of the universe, allowing researchers to infer its expansion rate and consequently its future trajectory. The cosmic microwave background, or CMB, is a remnant of the Big Bang, and by analyzing its temperature fluctuations, scientists can gather data about the universe's composition and geometry. Furthermore, researchers use the concept of dark energy, which is believed to be driving the accelerated expansion of the universe. By measuring the effects of dark energy on the movement of galaxies, scientists can refine their predictions regarding how this mysterious force will influence the universe's ultimate destiny. Another crucial approach involves the observation of distant supernovae, for measuring astronomical distances. By studying these explosions, scientists can determine how fast the universe is expanding and how this expansion rate has changed over time. The relationship between the brightness of these supernovae and their distance allows researchers to estimate the rate at which the universe is stretching out, giving them clues about its future. Additionally, galaxy clustering studies provide another layer of understanding, as the way galaxies group together reveals gravitational forces at play and helps predict how the universe's structure might evolve. Mathematical models, such as the Friedmann equations, are also essential tools for cosmologists. These equations describe how the universe expands over time, taking into account factors like matter density, curvature, and dark energy. By inputting current observations into these equations, scientists can simulate various scenarios for the future of the universe, whether it leads to a big freeze, big crunch, or big rip. Observations from telescopes, like the Hubble Space Telescope, have provided critical data that informs these models, enabling scientists to create a more accurate picture of the cosmos. In addition to these observational techniques, advancements in computer simulations play a vital role in predicting the universe's fate. Simulating cosmic evolution allows researchers to explore different scenarios based on varying initial conditions, examining how galaxies, stars, and other celestial bodies interact over time. These simulations incorporate complex physics, including gravity, thermodynamics, and radiation processes, allowing scientists to visualize potential futures of the universe in a more dynamic way. Moreover, gravitational wave astronomy has emerged as a new frontier,